I often get asked about pedigree analysis, and so I thought it would be helpful to make a video to go through the key points so that you can stop it and look at it many, many times. The most important thing to remember when talking about pedigree analysis is that it's a graphical representation of a pattern of inheritance for one particular trait, i.e. one particular gene. The code that is always used are squares for males, circles for females, filled in squares for an affected male, filled in squares, open squares and circles for unaffected organisms. This sort of process, that horizontal line, that indicates mating, and if you have two coming out from the same pair together as shown here, that indicates twins, although you don't see that very often. So let's first of all look at patterns of inheritance. So you can be asked to identify a pattern of inheritance using a pedigree analysis. And these words now become really important. So what does autosomal mean? Well, autosomal means a gene carried on chromosome 1 to 22. So our body chromosomes. Sex-linked means a gene carried on either the X or the Y, although it is obviously more usual for it to be on the X. Dominant means that you only need one allele to show the disorder, and recessive obviously means that you need two alleles to show the disorder. So let's have a look at some pedigree analyses. If we have a look at this example, we can use this example to try and establish whether or what type of inheritance is being shown here. So the first thing we do is we look at it and say, is there an even distribution of males and females? And yes, there is. So we can kind of assume that probably we are looking at something that is autosomal. Next, we want to look at where there are clear examples of parents going to offspring. And that little setup is quite interesting, and this little setup here is definitively interesting. So what we have here are we have two affected parents giving us an unaffected child. Now, what does this tell us about the parents? Well, it tells us that the parents must be heterozygous because they are having offspring that have a different genotype to themselves. And if they're heterozygous and affected and they're having an unaffected child, then that means that the trait must be dominant. So they would be, for example, big A, little a crossed with big A, little a, with the dominant here being expressed, leading us to learn that this must be a dominant autosomal inheritance pattern. Now, you can then sort of check that because here we have two unaffected parents and all of their offspring are unaffected. Here we've got an affected father and an unaffected mother having a mixture, so that does kind of make sense. If we now look at this setup, this setup, then what we can see is, if I ask my first question again, is there an even distribution of males and females? Well, you can see very clearly, no, there is not. It's very much only in males, and you can also see that it seems to be skipping generations. So what's happening here is this person might be X, little b, Y, say. So this mother doesn't have the disorder, so she's X big B, X little b, but that means that this son must be X little b, Y. So this tells us that it is sex linked and that it is recessive, because had this been a sex linked dominant trait, then all of this gentleman's daughters would have had the trait, because all of them would have received the dominant X chromosome from him. So when you're looking at sex-linked recessive traits, what you're really looking for is that it's in males and that you can see it skipping generations. And the final one that we're going to look at is shown here. And again, we're looking for certain particular setups, and this is our key setup here. So once again, we've got parents who are having a child with a different genotype. Now, that tells us that the parents, as I said before, must be heterozygous. So again, they would actually be big A little a crossed with big A little a. But in this case, the offspring that's got the disorder must be little a, and so that tells us that this is recessive and autosomal. And these patterns that I've just shown you are what we kind of look for when we're looking at pedigree charts, and they help us to determine whether the pedigree chart is showing what type of inheritance pattern that pedigree chart is showing. Now, if we apply this to a question, so this shows the pedigree for cystic fibrosis. Now we know that that is a recessive autosomal trait. We can see that also because of that setup anyway. So now we're being asked, what is the probability that this individual is a carrier of cystic fibrosis? So we know that what's happened here is we've had two heterozygous parents, and that we're asked what is the chance that this child will be heterozygous itself. So if you do a quick Punnett square, obviously that's homozygous, and this is heterozygous, therefore it is 50%, so it is B. We now look at this pedigree chart. This is simply asking for the pattern of inheritance here. So we've got a pedigree chart here, and you can see that we've got a setup of unaffected parents having affected offspring, and so straight away that tells us that it must be an autosomal recessive trait. And in this trait, it tells us in the question that this is a pedigree chart of an X-linked condition in which bone deformities occur. And now it's asking us to deduce whether the allele is dominant or whether the allele is recessive. Now here we've got two affected parents and they have an unaffected child. Now if they were both affected and this was recessive, we know it's X-linked, so he would be X little b y, she would be X little b X little b. So this person would be X little b y, so they would have the disorder. All of the offspring would have the disorder. So the fact that this person doesn't have the disorder suggests that it must be a dominant allele that causes the disease. And then it asks you, what would the genotype of this individual be? Well, again, you can see that this individual has got a daughter that does not have the disease, therefore they must be X big B, X little b. I hope that helps to explain a little bit about pedigree analyses and that you find this useful.